In this chapter, you guys are going to learn about thermal energy, thermodynamics. So, what is thermal energy? What is thermodynamics? Each time you see the word thermal or thermo, it has to do with heat. So, we've seen various forms of energy. We talked about potential energy, we talked about kinetic energy, uh, we talked about solar energy. There are various forms of energy, and thermal energy is another source of energy. And the easiest way to understand it is to think about energy that we obtain when surfaces heat up, when things burn. The energy we obtain from them is what we call thermal energy. So, in this section, what I hope you will learn is you will talk about temperature, absolute zero, heat, quantity of heat, the laws of thermodynamics, entropy, specific heat capacity, thermal expansion, and expansion of water. But in this specific lesson, we're going to go through temperature, absolute zero, heat, quantity of heat, and the laws of thermodynamics. All right, let's dive in. So, temperature. What is temperature? So, when we're talking about temperature, it is a measure of how of how hot or cold an object is. Like if you look at this image right here, when you touch somebody or if you touch a cup of tea and you touch another cup of water, right, you'll be able to feel that maybe the tea is hot relative to the water, right? So it is in terms of the person touching, right? It is relative. It is relative, and everything depends on the person's temperature. So depending on how warm or cold an object is, right? The measure of how or cold an object is what we call temperature. And we can use a thermometer to measure the temperature of an object or to measure the temperature of a body, right? Um, and the temperature of an object it depends on how much matter, right, that the person has. So it's kind of an average kinetic energy. So the temperature of an object is the average kinetic energy of all the particles in that object, right? So for us to actually calculate or measure the temperature of an object, we need to define a limit, define a lower limit and an upper limit. We need to define all of that. So temperature is proportional to the average translational kinetic energy per particle in a substance. So when we say the temperature of an object is 30 degrees, or let's say we say it's 70 degrees, everywhere on that object, if you take the temperature, if on any part of that object, it is going to be 70 degrees. Why? Because it is an average, right? It measures the average translational kinetic energy of all the particles in that substance. So because it is an average, temperature of an object is going to be the same for the same object on any part of that object. If you want to take your temperature, if you put your thermometer in your mouth, it's supposed to give you the same temperature than if you put the thermometer in your palms or if you put the thermometer in your armpits and all of that, because it gives you an average, right, translational kinetic energy of all the particle in your body. Now, if we're talking about a gas, we will say the temperature is going to be at how fast the particles are bouncing to and fro. So a gas that has a higher temperature, the particles are going to be bouncing faster than a gas with a lower temperature, right? And with a liquid, we'll say how fast the particles slide or jiggle past one another. Because in a liquid, remember, the particles are kind of not very far from one another, so at least they're able to slightly move past one another. But in a solid, we'll be talking about vibration because the particles in a solid are very close to one another, and so they only vibrate past one another. So how much they vibrate is going to be an indication of how much temperature they have, or how fast they vibrate is going to be an indication of how much temperature they have. Again, we use a thermometer to measure the temperature, right? So in every thermometer, you either have an alcohol thermometer or you have a mercury thermometer. So when you put a thermometer on an object, so what happens is the alcohol or the mercury will absorb the heat from your body and they will expand. And so how much expansion or contraction that the mercury or the alcohol is going to expand is a measure of how much temperature, or is a measure of your temperature. So the reading occurs when the thermometer and the object reach thermal equilibrium. So what is thermal equilibrium? So when you put the thermometer on your armpit to take your temperature, for the modern thermometers, as soon as it reaches thermal equilibrium, you will hear a beep. It will make a sound. Pim. That sound is to say that okay, the thermometer and your body they have reached the same temperature, because that thermometer wants to know your temperature. So if your thermometer doesn't reach your body temperature, then it cannot be accurate. So the point at which, or the temperature at which the thermometer and your body are the same, or they reach the same temperature, that point is called thermal equilibrium. Okay. So remember, infrared thermometers they operate by sensing infrared radiation. Okay. So now let's look at the different temperature scales. So if you look at the different temperature scale, you have the Celsius scale, right? It was named after Anders Celsius. Again, this is a very common scale, not very common in the United States, but common in the world of science. So for the Celsius scale, 0 degrees is the freezing point of water. So at 0 degrees Celsius, water will freeze. And 100 degrees Celsius is the boiling point of water on the Celsius scale. On the Fahrenheit scale, that was named after Gigi Fahrenheit, 32 degrees Fahrenheit is the freezing point of water, right? And 212 is the boiling point of water. That's on the Fahrenheit scale. Now, on the Kelvin scale, which is the SI unit for temperature, or the international unit for temperature, is the Kelvin. And it was named after Lord Kelvin. And so on that scale, 273 Kelvin is the freezing point of water, and 373 Kelvin is the boiling point of water. Now, the temperature that we call the absolute zero is negative 273 Celsius. It is a very, very cold temperature. Again, absolute zero is negative 273 Celsius. And what is the significance of that temperature? It is a temperature at which matter is believed to stop moving. So it is so cold. Remember that matter is always moving, but It is believed that at the absolute zero, matter stops moving, right? The kinetic energy of matter becomes so low or almost zero that matter will not be moving anymore. So the particles will not be vibrating, they will just be stay put. So it's a very cold temperature at which it is believed that matter will not have any kinetic energy. The ability to move will be almost zero. So the same size degrees as Celsius. So the Kelvin it has the same size like the Celsius on the scale. So the Kelvin scale is the same like the Celsius scale. And the Kelvin is a very important unit in science. In fact, it is the SI unit for science. So let's dive a little deeper into the theory of matter, the kinetic theory of matter. So what does it say? The kinetic theory of matter says that matter is made up of tiny particles, and these particles can either be atoms or molecules. Okay, so every form of matter, whether it's your clothes, whether it's a table that you're sitting on right now, whether it's your Chromebook, all of them at the nanoscale, they are made up of very small, tiny particles, and these particles are either called atoms or molecules, and they are always in motion. They are always. You might not be able to see, you might not be able to feel that the particles on your desk are moving right now because the motion of the particle is so slow that you cannot notice, right? But particles, whether it's on the desk, whether it's on the air that you breathe, whether it's on the phone that you use, those particles are always in motion. Always. Now, the total kinetic energy of the microscopic particles that make up matter, right, constitute what we call the thermal energy. Okay. So the total energy of the microscopic particle that make up matter are the kinetic and the potential energy. Okay. Now let's check this for understanding. There is twice as much molecular kinetic energy in 2 liters of boiling water as in 1 liter of boiling water, which would be the same for both. So the temperature, remember I told you that the temperature is the average kinetic energy of a particle, right? Is the average. And because it is the average, if you take the temperature of 2 liters of boiling water, it's going to be the same as the temperature of 1 liter of boiling water because it's an average. Okay. But what they are not going to have the same is their thermal energy. Because 2 liters of boiling water, because it has more matter, it will have more thermal energy than 1 liter of boiling water. But the temperature is going to be the same. Okay? The temperature will be the same because it is an average, it's the average kinetic energy. But the thermal energy is going to be different. More matter, more thermal energy. And 2 liters of boiling water has more matter in there than 1 liter. Okay. We've talked about the absolute zero, but let's dive deeper into it. So what we call the absolute zero or 0 Kelvin is the lowest limit of temperature. Okay, is the lowest limit of temperature at negative 273 Celsius. At this temperature, atoms or molecules have lost all available kinetic energy. A substance cannot get any colder. Okay, it is the lowest temperature. At this point, it is believed that particles cannot move. Remember, the energy of motion is called kinetic energy. And so if particles cannot move, it means they are believed to have lost all their kinetic energy. All. So again, the lowest temperature is negative 273 Celsius or 0 Kelvin. Atoms or molecules have lost all available kinetic energy, and the substances at this temperature cannot get any colder. As temperature of a gas changes, the volume of a gas changes. Okay? At 0 degrees Celsius with constant pressure, volume changes by 1 over 273 for each degree Celsius. So what we are trying to explain here is that when you heat an object, it expands, it increases volume. And when that object is cold, what happens? It contracts, it reduces volume. Okay. So the absolute zero or 0 Kelvin again is the lowest limit of temperature. Molecules are believed to have lost all available kinetic energy. So now let's talk about thermal energy. So again, I said thermal energy is a form of energy. Again, it is heat energy. So if you look at this boy right here, he's burning an object. Okay, so when he burns that object, heat is released, thermal energy is released. Okay, so the temperature sparks very high, 2000 degrees Celsius. A lot of energy per molecule of spark. Total energy is small due to relatively few molecules per spark. Low transfer of energy. So what you need to understand here is that thermal energy is dependent of how much matter you have. So if you are burning a very little object, it is going to release a small amount of thermal energy compared to a larger object. Why? Because more matter, more thermal energy. Less matter, less thermal energy. So what is heat? Okay? What is heat? So we define heat as a flow of thermal energy due to a difference in temperature. For example, if you give a handshake to someone, if you guys are holding your hands and you guys have different temperatures, heat is going to flow from the person that has a higher temperature to the person with a lower temperature. Because the person that has a higher temperature has a higher thermal energy, and the person with a lower temperature has a lower thermal energy. So heat is going to flow from the person with higher temperature to a lower temperature. So that flow of thermal energy due to difference in temperature is what we call heat. So the natural direction of heat flow is from a higher temperature substance to a lower temperature. That's the direction in which heat is going to flow. It is never going to flow from a lower temperature substance to a higher temperature substance. It is always from a higher temperature substance to a low temperature substance. So 1 liter of water in a left pot, right here, and then there's 3 liters in the right pot. Both pots absorb the same quantity of heat. If both pots absorb the same quantity of heat, the temperature increases 3 times as much in the pot with a smaller amount of water. So if these two they absorb the same amount of heat, you will see that the temperature is going to rise faster. The thermometer, if you look at the mercury rises faster in this one compared to this one. Why? Because the particles here are smaller. Okay, so they will heat up faster than this one. Okay, so it's the same thing if you're trying to boil water and you put water on a stove. If you put a small amount of water, it is going to boil faster than a large amount of water. That's the logic. because a large amount of water will take more time. There are more particles that need to absorb heat to get for their temperature to increase. When the same amount of heat is added to each of the two containers of water, the temperature increase in each will be, the temperature cannot be the same, okay? The temperature is always going to depend on the amount of water in each. The more water, the less faster the temperature is going to rise. So the quantity of heat. Heat is energy in transit. It is the measured in unit of energy joules. So remember the unit of energy is the joule or the calorie. So if you look at your bag of chips or your bottle of juice, you will see that it tells you how much energy in calories you will obtain if you eat that one bag of chip or if you drink that bottle of water. So it's defined as the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. So if you put water on a pot and you put it on a gas stove and you're trying to heat it up, the amount of energy that 1 gram of water is going to need for its temperature to change by 1 degree Celsius is what we call the specific heat capacity. Okay, and for water, that temperature is about 4.19 joules. And so if you look at the conversion between joules and calorie, 4.19 joules is equal to 1 calorie. That's a conversion factor. So 4.19 joules of heat will change the temperature of 1 gram of water by 1 degree Celsius. So now let's look at the energy rating of food or fuel. So they are measured by energy released when they are metabolized. So when you heat food, when the food is heated or broken down by your system, that's when the energy is released. And so we have the kilocalorie. Kilocalorie simply means 1000 calorie because kilo is a prefix that means 1000. So if you look at the food that you eat, actually, even though it says calorie, but because the calorie is in capital letter, each time you say capital C, calorie in capital C, it actually means kilocalorie. So we either say 1 kilocalorie or 1 calorie if the C is a capital letter. Is the heat needed to change the temperature of 1 kilogram of water by 1 degree Celsius. All right, so we'll summarize the quantity of heat. Heat is energy in transit. Heat is measured in joules or calories or capital calories. One food calorie equals 1000 calories. To the Weight Watcher, the peanut contains 10 calories. Okay, so in this case, this is 10 kilocalories because the C is a capital letter. To the scientist, the peanut releases 10,000 calories. You see, this is small c. Okay, so 41,900 joules of energy when burned or digested. So these are different ways of converting. So it can be 10 calories with a capital C, or you just say 10,000 calories with a small c, or you just convert that to joules and it gives you 41,900. So let's check for understanding here. The quantity of heat needed to raise the temperature of a certain substance, a specific amount is 1 calorie. This is the same amount of energy as, okay, take note, 1000 calories or 4.19 joules. So remember 1 kilocalorie is equal to 4.19 joules. You heat half cup of tea and its temperature rises by 8 degrees Celsius. How much would the temperature rise if you add the same amount of heat to a full cup of tea? So again, because you've doubled the amount of matter, you are going to have half the temperature. Okay? When you double the amount of water, the amount of the temperature is going to drop to half because the, it is an average. It's like you have 20 people in a classroom and I'm trying to share you guys cupcakes. If I have 40 cupcakes, you guys will all have two cupcakes. But if the size of my classroom doubles to 40 to from 20 to 40, now the 40 cupcake is going to be distributed to everybody. And so you will realize that I will ask each and every one of you to share your cupcake, and you will find yourself that you realize that the number of cupcakes that you had will halve because the size of my classroom has doubled. So now let's look at the laws of thermodynamics. The laws of thermodynamics. Thermo, right, means comes from heat, and dynamics means movement. Okay, so you can now link thermo and dynamics. Okay, so is a movement of heat. So the laws that govern the movement of heat, because thermal heat, dynamics movement. Okay, so there are about three of these laws, and the first law of thermodynamics, what it says is that when heat flows to or from a system, the system gains or loses an amount of heat equal to the amount of heat transferred. In simple words, what this law says is that you cannot create energy. Okay, you cannot destroy energy. Energy is never created, is never destroyed. You can only transfer it from one form to another. So if you take food and you eat, your body breaks down this food and the food is changed. The energy in the food is changed into chemical energy, right? And when you heat it, for example, the chemical energy in the food when you eat is changed into sound energy when you speak, is changed into kinetic energy when you walk or run, is changed into potential energy when you're standing. So the energy in the food is not lost. It is just changed from one form to another. So that is what the first law of thermodynamics is kind of explaining, that you cannot change energy, you cannot destroy energy, you cannot create it. More specifically, heat added to a system is equal to the increase in internal energy plus the external work done by the system. This kind of deep. We will not go into this detail. Okay. So energy can neither be created nor destroyed, but it can be transferred from one form to another. That's a summary of the first law of thermodynamics. And that's what I expect you to know. Now, with the second law, it's a second law. So this law states that heat never spontaneously flow from a cold substance to a hot substance. Okay. Remember, I told you here that when two objects are in contact, heat is going to flow from the object that has a higher temperature or that's hotter to the object that has a lower temperature or that's colder. That's what the second law of thermodynamics is trying to explain, that you cannot have a spontaneous heat flow from a cold object to a hot object. In summer, heat flows from the hot air outside into the cooler interior of a dwelling. That's why when you're sitting inside, you feel it, you say it's hot. Because during summer, the hot air will flow into your house that has a colder dwelling or colder air. And that's the reverse in winter. Okay. What happens is that the heat inside the house is usually hotter than that outside. So it's going to flow from the inside to the outside. That's why, because you're losing that heat, you start feeling cold. Okay. Heat can flow from hot to cold only when work is done on the system or by adding energy from another source. That's why we say it can never be spontaneous. Spontaneous means you do nothing to it, it just happens. It just happens. So you cannot have heat flowing from a cold to a hot spontaneously. It just doesn't happen on its own. That's what it means by spontaneous. Now, the third law of thermodynamics, what it says is that no system can reach absolute zero. So even though we talk about absolute zero, but we're just imagining that temperature. Okay, we're just imagining. No system has ever reached that temperature so far. So let's check for understanding. When work is done on a system compressing air in a tire pump, for example, the temperature of the system will obviously increase. Okay, when you do work on a system, for example, an example of doing work on a system is compressing air in a pump or compressing air in a tire. Okay, it increases the temperature of the particles. When a hot cup is filled with cold water, the direction of heat flow is from the cup. When a hot cup is filled with cold water, the direction of heat flow is from the cup to the water. So the cup is hot, right? It is going to give or supply its heat to the water because the water is colder. So always remember, for the second law of thermodynamics, heat flows from the hotter object to the colder object. It is never going to happen spontaneously in the reverse direction. All right, so that's that for this specific lesson, and I will see you in the next lesson. I hope you enjoyed.